Okay, so this is the last part of chapter 20 on transition elements and coordination chemistry. And so here we're looking at bonding and transition metal complexes, right? So we can see that if you have the vacant metal ion or atom, it's got a hybrid atomic orbital, and the ligand has some pair of electrons that are able to move into that vacant space and create a covalent bond. So that's why we say that like this is more of a covalent relationship, because we see a sharing going on between the ligand and the metal. It's not a total transfer like it would be in an ionic system, at least for most ligands, those ligands that bond more in that sort of way. There are some ligands, like we've seen before, that bond more ionically. But when we talk about geometry, we're using the same geometries as we would have used previously in like a 151, like sp2, sp3, etc. With the important note being that we will see these higher order hybrids like the D sp3 and the D2 sp3. And here the position of the D, whether it's in front or after the sp3, will be used to determine the relative energy. Like if it's using a D3 and then this is like a 4s and a 4p, or whether this is like a 4s, 4p, and a 4d. Like they'll use that to figure out which D is on that side. And we'll see that we can use magnetism to kind of figure out which side the D would actually be on. But all like 6 geometries are going to use a D2 sp3. We'll see a little more about that. We've got some pictures here again. This is for a square planar, and this is for the octahedral type arrangement. But these are the same hybridizations we've seen previously. It's just that now we can make a distinction between these two. The book discusses that, but it talks about how that has to be measured empirically. So they look here at a free cobalt 2+ ion with the electron configuration here. That's its configuration, so we write that down. And then we bring in the ligands, right? So each ligand is going to donate two electrons for each pair. So there's 4 of these, so they'll each donate 2 electrons into the space. And because this is in sp3, they're not even going to fill and touch the Ds. So we can translate this hybridization into an electron diagram. Again, I'm not going to test this too heavily. My point is just being able to really look at this and see that this is paramagnetic because the electrons are not all paired up. And remember that paramagnetic substances contain unpaired electrons in their configurations, and they're attracted by magnetic fields weakly. And if they're all paired up, then that's a diamagnetic, and they're repelled weakly by magnetic fields. So they look here at a square planar complex, and these are unpaired with the free N2+ ion. And they show how this one is dsp2. So we use one D, and then an S, and then 2 Ps, and they'll go in that sequence. And that way they'll all be able to fill up, so each of these 4 cyano groups can all fill in that direction. This makes this diamagnetic because all the electrons are paired. Here we have an example with the higher directionality, right? They say it can be one of the two, and they say this needs to be paramagnetic according to measurements. So we'll need to pull these 2 Ds preferentially over these other 2. Otherwise, we'd be leaving these two open, but we wouldn't be maximizing the spin if we transfer these over here, because we've got these 4 electrons. See, that would make this all diamagnetic if we took these 4 and paired them up. But they say experiments show it's paramagnetic and has 4, so that helps us figure out that evidently none of the 3D orbitals are available to share. So they must be using the 4D. Again, I'm not really going to be looking for you to make that distinction per se, but just to be able to know that if you've got a paramagnetic system, they're not paired, and if they're diamagnetic, they're all going to be paired. So this is, again, paramagnetic. And we see here 6 D2 sp3 bonds to the ligand, so 2 Ds, an S, and 3 Ps, being able to see this, right? Complexes of metals like cobalt 3+, they exhibit more than one spin state are classified as high and low spin. So the high spin is where the D electrons are arranged according to Hund's rule to give the maximum unpaired electrons, so not like this version, so there's no unpaired electrons. Low spin, like this example up here, is one where they've paired up. So there's kind of a contention between these two, right? Because Hund's rule, our conventional understanding of what makes a good electronic configuration, would tell us to maximize the number of unpaired electrons. But we have a tendency to try to close up the d orbitals and other orbitals because we get a stability bonus when we can have fully filled or half-filled shells. So there's a tendency to try to occupy when that's the closer way to go. And then that may be a more stable configuration. So that's where the stability for low spin systems kind of comes into play. Again, key for you to know here, we'll be looking at the So here they've got these ammonias, right? There's 6 of them. Each of them brings in 2 electrons each. They say they want me to set up a configuration, and this is octahedral, so it must use one of those 2. They say it's preferred to use the lower version because that's got a lower energy and there's a lot of vacancies here. We can do it and make everything be keep it being paramagnetic here, because we've still got these 2 unpaired ones. It would still be paramagnetic even if we open the one on the other side, but the reason they're saying this one is prepared is due to lower energy. Again, I'm not going to test you on being able to distinguish these 2 cases, but you should understand sort of the rationale behind one or the other. So now we'll delve a little further into crystal field. This is one of our last topics here. So crystal field theory looks at bonding in complexes as arising from electrostatic interactions and considers the effect of ligand charges on the energies of the d orbitals, right? So this is where the d orbitals can split. And we talked a little bit about this when we looked at the spectroscopy at the end of the last section. So here we're going to look a little more closely at that in particular. So if we look at this octahedral complex, they say that according to crystal field, the bonding is ionic and involves electrostatic attraction, right? So the ligands have to repel each other, so they optimize to form an octahedral geometry, right? And the metal ligand attraction is greater than the ligand-ligand repulsion to create a stable configuration, right? And the reason they're looking at this as a more so ionic system is that we have an overall charge, like everything is overall charged here. But we can say that in valence bond theory, we look at this as being covalent in nature and sharing, whereas in crystal field, we typically are looking at there can be some of both going on, or there are different ways to think about it, right? Because in a complex like this, it's understandable that this could be thought of as more so directly ionic, because the charges balance each other out. You could almost think about it like a little ionic grouping, and that would make sense here. Whereas it doesn't make sense like when we have neutral molecules brought in. Like there's not really any kind of ionic justification for that. And yet at the same time, this does adopt the geometry, and we can still think about this like a complex as well. Like I say, some complexes have more ionic and some complexes have more covalent bonding, and both of those are necessary, and that's where the valence bond versus crystal field kind of come into play here. Complexes that contain neutral dipolar ligands, they say the electrostatics are more of an ion dipole type, so this is more like a covalent interaction, but you know, there can be both going on at the same time in the same complex and with different, it often depends on the ligands. So they look at how these ligands arrange themselves in space to form the different configurations and shapes dictated by the d orbitals. These are our d orbital diagrams, and then the crystal field of the octahedral setup, and the metal ion and the ligands are regarded as charged particles held together by attractions. And the ligands pull the different orbitals of the d space into a particular shape that's also associated with the bonds of the ligands themselves. And as they say, this tends to result in a splitting, okay? The d, z squared, and d, a little different from the other two. These 3 all lie on the plane, different planes and orientations, and these do not. But the d, x squared minus y squared point directly at ligands. They fit up a lot better with the ligands than these do. These don't point as directly at the ligands. And these lobes fit also directly onto a ligand space. So these 2 tend to have better overlap with the ligands, kind of makes more sense. And these 3 seem like they should always generally be degenerate because they're just rotated around an axis. But these 2 make sense to be separate from them because they're not in any way like just a rotation of the other ones above. So typically we see a splitting, right? In this case, we see a splitting where the z squared and x squared minus y squared are in a higher energy. But that's not always the case for all versions of crystal field and crystal field splitting. Sometimes they get raised to a higher energy, and sometimes they're at a lower energy. And it can depend on the exact version of the crystal field. Typically it looks like this, where they're split that way, but it's not always the case. They consider this complex, and they say we put the d orbitals in one of the lower energy versions. They denote them by their subscripts. And usually there's 2 groups, one with 2 and one with 3. and then a light interaction can be set up by the energy difference between these two, and we could measure that by the color that the complex ends up being. So we can think about the free metal ions as having degenerate d orbitals, degenerate here meaning all equal in energy, and then the interaction with the ligand splits them. Okay, and sometimes these two, the two above, are below these three, sometimes the three are above, but they're always in this kind of categorization. dz squared and then x squared minus y squared are always together, and then these are always separate. Because those orbitals point differently toward ligands. One is between ligands and one is pointed directly at ligands. Typically these two are higher in energy and these are lower, but that's not 100% the case in every ligand scenario. So they're modeling that though in this direction, and then we can measure that, and they say that like different field strength ligands can produce bigger or smaller gaps depending on which ligands are with it. Water is a relatively smaller ligand field generator than these higher up ligands, which cause the gap between these two to be bigger. And that's how crystal field models the system. So with this, you could say that like the color of the ligand, like the color of the complex is going to change with the ligands. So as you put different ligands on a complex, the color changes through the spectrum. And they've built this kind of spectrum of ligands based on this. And what's interesting about these ligands is that they, later on, when you get more into an organic class, you can think about them also with organic terminology as nucleophiles. And that there's a correlation between these weak and strong field ligands and weak and strong nucleophiles, because they're seeking something positively charged. All of these they're all Lewis bases, and they all have free electrons that can go into something positive. So they're all, in that sense, seeking a positive, seeking a nucleus, and that's where that name comes from. So they're not only Lewis bases and ligands, but they can also later they'll also be called nucleophiles, and they follow the same basic rule system. That's what's interesting about this. So that's where you get the bigger differences. They talk about D10 ions. Main group ions have partially filled D. They can't undergo DD interactions, and most of them are colorless. So the strong colors, which we saw at the beginning of this chapter of transition metal complexes, typically come from crystal field splitting. And this is why that happens. And they can see how a high spin and a low spin can have differences depending on which determines which of the spins has lower energy. In general, when an electron moves from z squared or x squared minus y squared orbital to one of the lower energy ones, the orbital energy decreases. So having more electrons down there tends to help you out there. Because of electron-electron repulsion, it costs energy to put an electron that is in an orbital that already contains an electron. So there's some additional space there. The choice between the high spin and low spin configurations arises only for complexes that have 4 to 7 Ds. So there can be different ways, okay, and they say all 6 d electrons are spin paired in the lower level before they go to the higher one. And it depends on the size of this gap can also control whether they're high spin or low spin. Low spin can be if you have a bigger gap where it's harder to access the higher orbitals, and if you could get a high spin if you have a smaller gap, because then they'll all populate. So this is the scenario where they act more like they're degenerate because the gap is smaller, so you fill them like you would fill normal d orbitals, but with a bigger gap they don't all fill. That's the basic principle they're getting at here. And they talk a little bit about other kinds of complexes, tetrahedral and square planar complexes, where you don't have access to all of these orbitals, right? So they say this is the opposite. So here's where the x, y, z, x, z, and y, z will have higher energy. So again, like we talked about, different complexes will have different ordering. So the octahedral complex, the energy ordering follows the relative orientation. They don't derive the result. But the point being is that in square planar systems, the relative map is different. Okay, in a tetrahedral complex, they'll be in this orientation. It tends to be larger in square planar, and these configurations different. So this is why, like I said, in a complex, sometimes these x, y, x, z, and these are higher in energy than the other ones. It depends on the shape of the complex and the relative size and overlap of things, how big these gaps are. So in a square planar versus a tetrahedral, the shape is different. Again, I'm not going to ask you to memorize these shapes in particular. Again, the idea is just to know that these two different shapes do exist, and that a tetrahedral complex and a square planar complex do not have the same crystal field splitting. they have different geometries. And that's the note they make there, so that you can make a note to be able to do some of these problems. So they look here, so this one's got 3 around it, but that actually ends up being so it has 3 unpaired electrons, and in a complex, they occupy the 3 lower sets. So they draw that one down below. In the next complex, they say, okay, these can have a high spin or low spin because it's a strong field ligand. All 4 d electrons go into the lower. Again, a lot of these scenarios I'm not going to ask you about in great detail, but you should be aware of the relative rules and ideas here to be able to make estimates like of which ligand is a higher energy, higher ligand field, and such like that. I'm not going to have you draw these diagrams out in incredible detail on a test. Being able to just see which one is more likely to be like a high spin or low spin, or which one has ligands that are strong ligand field or weak ligand field. I'm going to ask more questions like that as opposed to asking you to draw diagrams like this. You should know how to do these. You should review these in a homework, but just know I'm not going to ask these in great detail because there are a lot of little factors that go into each individual example, and so you may not always necessarily be aware of them from each particular way they present it. Like I like this last one where they have a high spin configuration because this is a weak field ligand, so you know the gap needs to be brought together. This is octahedral because you've got 6 of them, so you've got all the kind of simple examples. So C, I think, is a relatively simple example. C and B both are relatively simple examples, whereas here, because you've got 3 and you got to think about whether it's bidentate or whatever, that's an additional complication I'm not going to really stress into this example here. But I do think that examples like B and C, where they put in pairs of electrons and they set up this way, these are easier to understand from the metal standpoint space, and kind of see where they're all going to end up going out here. Has this high spin configuration, so you can get a general sense, but you don't have to necessarily draw all these out. This is more of the shapes with the populated d electrons and everything else. So again, they look at a crystal field energy diagram and predict the number of unpaired electrons. So this is again about predicting. So you got 5 d electrons in iron 3+, distributed between higher and lower. This is a tetrahedral, so we can pull the configuration from the stuff we just looked at. And square planar, we can pull that diagram from here as well. So they distribute these 5 electrons into this space, and then you get something that looks like this. Because the energy gap here is small, they have this one as a complex B with additional electrons. They show you how this one has 8 d electrons. And so they fit those 8 d electrons into here, filling the lower ones up first. And because of the large gap, they say there's no unpaired electrons. So basically, it's just about using the correct map. And like I say, I'm not going to ask you to memorize these maps, so I'm not going to go into too much detail. You should just generally know them. But I'm not going to ask particular questions for you to draw these like this. Maybe I'll have a question where you can say which one's more likely to be something or something else, where knowing this map would be really assistive, but I'm not going to ask you to draw them per se like this. The last part talks about fixing nitrogen, doing nitrogen fixation, and what I thought was really interesting about this is the enzyme that's used to facilitate this process. We talked about the Haber process before in previous chapters, which converts elemental nitrogen and hydrogen into ammonia, but we have to do this at like 400 to 500 degrees and extremely high pressures in the presence of some kind of catalyst. But living things are able to do this in the root nodes of plants and fixing nitrogen in the atmosphere without additional presence of hydrogen gas or anything like that. So the question is, how are they able to do that? Well, if we look at the enzymatics of this, there's an enzyme called nitrogenase that catalyzes the reduction of N2 to NH3. These have been studied in great detail, and they don't just use iron, they use another transition metal like molybdenum or vanadium as well, which is really interesting. We typically don't see living things using rarer metals like those, but they are able to utilize them in these kinds of environments. And they look at the active site, right, and they're looking at this in terms of, how can we think about it as a coordination complex, right? They say the molybdenum atom is surrounded by 3 sulfur ligands and other donor atoms. The Fe7 molybdenum sulfur 9 cluster is believed to be the active site where the N2 is reduced. Precisely is not known. The book's maybe a lot of dates, so maybe we do know now. The iron molybdenum protein has all the machinery needed to break the strong N and bond. It's a triple bond to produce the NH3. Requires a steady stream of electrons, 6 electrons, to break each bond. With the help of the organic molecule adenosine triphosphate, ATP, horsepower used in the cell, electrons are pumped from a series of 1-electron steps from the iron protein through a chain. Compounds such as diamine and hydrazine have been suggested as intermediates, but the exact reaction mechanism is still unknown. So they show this as, we can imagine this as a transition metal complex that involves these two irons, and they've got this carbon center here, and they've got this structure all around it with sulfurs and various things. So decoding this process would involve thinking about this active site of an enzyme as a coordinate complex. So we can model it as a coordinate complex. It's got all kinds of other protein parts and stuff stuck around it, but the active site itself is just a coordinate complex. So if we can understand it in that sense, there have been other instances, not this one, where we have been able to successfully use that and then replicate it and build catalysts based on how living things do it by studying the coordination complex chemistry of what's going on at the site. So anyway, so this is the end of chapter 20. Hope you found this very edifying, and I will see you all in the next one. Thank you.